Hi, we are going to continue our discussion about geometric modeling. Having finished the examination of curves, now we are going to get acquainted with two-dimensional subsets of the three-dimensional space called surfaces. So a surface is a two-dimensional subset of the three-dimensional space. To define it, we need equations similarly to curves. And again, we have basically three options to establish that equation. The equation can be explicit when we express one Cartesian coordinate from the other two. This equation would be very straightforward, however, it's too restrictive, so we cannot use it too often. One notable exception is terrain modeling, because in maps, this kind of strategy is applied. In a map, we assume the xy plane to be the sea level, and for every xy pair, we specify the height of the terrain at that particular point. With this notation, not even caves can be modeled, and we would also fail to represent a complete sphere with this explicit representation, because for a particular pair of xy values, we would typically have 2 or 0 number of z values. So instead of the explicit equation, we prefer implicit equations, which means that we do not require one of the Cartesian coordinates to be expressed from the two, but the three Cartesian coordinates participate in an algebraic expression, which is usually organized in a way that on the left-hand side we have a function of these Cartesian coordinates, and on the right-hand side we have 0. If we start with the geometric definition of classical surfaces and translate this geometric definition to equations using the language of vector algebra, we usually obtain an implicit equation. This is an example of the implicit equation of the sphere, where the center of the sphere is defined by Cartesian coordinates cx, cy, cz, and the radius of the sphere is just r. The plane equation is also expressed in this form. Here, a, b, c are the components of the normal vector of the plane, and d describes the signed distance from the origin and the plane using the units of the normal vector. Similarly to curves, we can also express surfaces in parametric form. In the case of curves, we made an analogy between the parameter and the time and imagined the curve itself as a motion. As surfaces are two-dimensional objects, we will need two free parameters instead of the single parameter of curves. It means, unfortunately, that we will not be able to imagine the set of points as a kind of motion. Instead, we may imagine a surface as a composition of two independent motion. One is parameterized with u and the other is parameterized with v. An example of this parametric form is the sphere again, which uses the latitude and longitude angles typically applied on the Earth. If we want to express an origin-centered unit radius sphere, then a point on this sphere can be unambiguously defined by two angles, angle V, which is in between the north direction and the direction of the point, and another angle U, which is in between the projection of the direction of the point onto the xy plane and x is x. Knowing these two angles, we can express the Cartesian coordinates of the point on the sphere, because here we can find a right triangle. The hypotenuse is 1, because we assume that this sphere has a unit radius. So this leg is of length cosine v, and the other leg, which is projected onto the xy plane, is sine v. This leg should be projected further onto axis x and axis y, and this projection introduces a multiplication with cosine u for coordinate x and with sine u for coordinate y. So these cosines and sines define an origin-centered unit radius sphere. If we want to have a sphere with radius r, then this unit radius sphere is scaled up with r, and if we want to have a sphere with center cx, cy, cz, then translation should be applied. So generally, x, y, and z are functions of the two free parameters, latitude and longitude angles. These parameters in their respective domain, u can run along the equator and v from the North Pole to the South Pole, so u can take any value between 0 and 2 pi, v only values in 0 pi. Implicit equations are typically obtained when we translate the geometric definition of the surface to equations using the language of vector algebra. Let us consider specific examples of those surfaces where the resulting equation will be a quadratic equation in the xyz Cartesian coordinates. The first example is the sphere again. So we start with the geometric definition of the sphere. The sphere is the collection of those points where the distance from the center is equal to r. So let us translate this definition using the language of vector algebra. The distance can be obtained by first computing the difference of the two position vectors and calculating the absolute value or the length of this vector. And this length must be equal to r, the radius. Our second example is the ellipsoid. The geometric definition is the following. So we consider those points R as points of the ellipsoid for which the sum of the distances from two focal points f1 and f2 is equal to a constant c. Again, the distance between 2 points can be obtained by finding the difference of the two position vectors and calculating the absolute value of this difference vector. The hyperboloid is quite similar to the ellipsoid. The only difference is that instead of adding the two distances, here we calculate their difference. And this difference must be equal to a predefined constant c. Finally, the paraboloid is the set of those points where the distance from a focal point f is the same as the distance from a plane defined by position vector p and unit normal n0. The distance from point f can be obtained by calculating the difference vector and the magnitude of that difference vector. Assigned distance from a plane can be obtained by inserting the position vector of the point into the plane equation, having converted the normal vector to a unit vector. This is assigned distance, so it has a positive value when the point is on that side of the plane where the normal vector points, and negative on the other side. Therefore, we take the absolute value of this scalar. In these example equations, the absolute value or the lengths of vectors show up, which means that these equations include square roots if we express them in Cartesian coordinates. We do not like square roots, we try to get rid of them, and it is possible if we compute the square of the two sides of this equation. Perhaps we should do it 2 times when there are 2 absolute values in the equation, but in the case of these examples, we always get a second-order equation, which means that all the mentioned examples can be expressed in a general form, so-called quadratic form, when the x, y, z Cartesian coordinates are extended with a constant 1. So this is a 4-element row vector, and we use it again as a 4-element column vector, and in between the row vector and the column vector we insert a 4 times 4 matrix that contains the scalar parameters describing the scalar of x squared, xy, xz, and x, and so on. it is always possible to express this 4x4 matrix as a symmetric matrix. So we can say that all possible ellipsoids with arbitrary center, arbitrary orientation, and similarly all possible paraboloids, hyperboloids, cylinders, and so on can be expressed in the same form. This is very useful because if we implement operations on this general quadratic form, then these operations will be automatically applicable for an arbitrary ellipsoid, paraboloid, hyperboloid, cylinder, and so on. So we solve their problems at once with a single implementation. I inserted here example equations when, for example, the ellipsoid is in a very special arrangement when its center is the origin of the coordinate system and the axes of the ellipsoid are the axes of the coordinate system. But I want to emphasize that this quadratic form is applicable not only for such special ellipsoids, but these ellipsoids can be anywhere and can have any kind of rotations. When our surfaces will be rendered, we will need the normal vectors at particular points on the surface because these normal vectors play an important role in the shading calculation. So our task is to determine the normal vector of an implicit function f at a point represented by Cartesian coordinates x star, y star, z star. The answer to this question is that the normal vector for implicit surfaces is just the gradient of the normal vector evaluated at the point of interest. Why is it so? Let's consider the surface. So we take the equation of the points of Cartesian coordinates x, y, z that are on the surface and assume that these x, y, z Cartesian coordinates are in the neighborhood of a given point x star, y star, z star, and this given point is also on the surface. So let us express x as x star plus a small offset x minus x star, and similarly y is y star plus a small offset y minus y star, and we do the same for z. As the three offsets are small, we can use the Taylor's approximation. The Taylor's approximation for a three-variate function looks like this. We have to evaluate the function at point of Cartesian coordinates x star, y star, z star, which is here, then the first derivative of f with respect to x, which is multiplied by the offset in x. The first derivative with respect to y is multiplied by the offset in y. And finally, the first derivative with respect to z is multiplied by the offset of z, and these terms are added together. The first term is 0, because we assume that x star, y star, z star identify a point that is on the surface, so these Cartesian coordinates satisfy the equation of the surface. Concerning the remaining terms, which are expected to be equal to 0, we can observe that this is a linear equation for free Cartesian coordinates x, y, z. We may ask what kind of surface this is. This is a plane if it has a linear equation. This equation can also be rearranged and expressed in a vector form, so we can take the three partial derivatives and put them in a vector. The three offsets form another vector, and this formula is nothing but the scalar product of these two vectors. Let us compare this expression with the equation of the plane. The general equation of the plane looks like this, where m is the normal vector of the plane, r is the running point on the plane, and p is one particular point on the plane called the position vector of the plane. Making correspondences, these three partial derivatives, called the gradient of f, is the normal vector, r represents x, y, z, the running point on the plane, and p represents x star, y star, z star. one particular point on the plane. So indeed, this is a plane, and we also know that the gradient is nothing but the normal vector of this plane. For curves, it was very useful to imagine curves as motion and express them in parametric form. It can also be done for surfaces, but as surfaces have two free parameters, we have to think of two independent motions. There are different strategies to do that. One interesting strategy is called extruding. We trace back the definition of the surface to the definition of two curves for which the motion analogy can be used. So in case of extruding, we have two curves, a profile curve and a spine curve. From these two curves, we obtain a surface by moving the profile curve along the spine curve. And during that movement, the profile curve sweeps a set of points. The swept set of points are considered to be the surface by the definition of this extruding operation. Okay, this is pretty straightforward, but what is the equation of the resulting surface? Let us consider one particular v value. So when the sweeping operation is here and the swept point is here on the profile curve, from the origin of the coordinate system, we have to apply the translation of the profile curve, which means that the origin of the coordinate system should go to the point on the spine curve identified by parameter v, and from here we have to visit the profile point identified by u. The resulting point will be the sum of these two vectors, so we can conclude that extruding is just the simple addition of two curves parameterized independently by the two free parameters of the surface. For example, if the profile curve is a circle and the spine is a spline curve like this, the resulting surface would look like this. It's not so nice that the cross-section area gets smaller in these parts. It could be solved by not only translating the profile curve, but also rotating in a way that the plane of the profile curve is always perpendicular to the tangent of the spine. And finally, we can generalize it even further and allow even the modification of the profile curve as it travels along the spine. For example, this torque is also an extruded surface, but the orientation of the plane of the profile curve changes from point to point, and also the definition of the profile curve is modified as we are at another point of the spine. There is another technique which is similar to extruding, but now instead of a translational motion, we will rely on rotation. Suppose we want to design a champagne glass to celebrate something. First, the contour or the silhouette of the champagne glass is designed using the well-known strategies of curve design. So we can use, for example, Catmull-Rom spline, placing control points of this curve and relying on the Catmull-Rom algorithm to find cubic polynomials that interpolate the control points. Now we assume that the curve is a planar curve and it is in the plane defined by axes x and z. The parameter of the curve is denoted by u. Having obtained the silhouette curve, we are going to rotate it along axis z and consider those points that are swept by the contour curve during the rotation. Let us look at the situation from the top into the direction of the minus z axis. Selecting one particular point at the end of this green arrow, when rotation happens, this point moves along a circular path. The angle between axis x and the current position of the circular motion is denoted by v. We know the parametric equation of the circle. It is radius times the cosine of the angle V and radius times the sine of the angle V. The radius is just the length of this green arrow. So using this radius information, we can express x and y coordinates as functions of parameter u, identifying the curve point, and parameter v, representing the circular motion. When points are rotated around axis z, the z coordinate doesn't change, so we just copy the expression of the z coordinate from the curve to the z coordinate expression of the surface. Finally, we are done. We expressed the x, y, z Cartesian coordinates of surface points as functions of u and v surface parameters. The champagne glass is ready, so we can open the bottle. In case of parametric surfaces, we also face the problem of the computation of the normal vector at a particular point on the surface. The point is identified by parameter pair u star and v star, and we are here on the surface. A surface point is identified by two free parameters, u and v. Let us fix the first parameter from these two free parameters to u star and allow the second parameter to run in its appropriate domain. We will have a function where the input is a scalar value v and the output is a point in the three-dimensional space. These scalar variate vector-valued functions or curves, but instead of t we denote the free parameter by v. This curve is on the surface because it has the same form as the surface equation for arbitrary u star v pair. On the other hand, this curve also goes through our point identified by parameters u star and v star because somewhere v takes the value of v star. We know that the velocity of a motion is always tangent to the path of the motion. The velocity is the time derivative. Now, the role of the time is played by parameter v, so we have to take the derivative of the surface function with respect to v. And the result is a vector which is tangent to the curve, so it is in the tangent plane of the surface at point identified by parameter pair u star and v star. So we already have some information about the tangent plane, but this information is not enough because there are infinitely many planes that contain this computed tangent vector. However, we have another parameter too. Let us play the same game by fixing parameter v to v star and letting u to run in its domain. Again, we are going to have a curve that is on the surface and goes through the point of interest, and here we can compute a tangent vector to this yellow curve with differentiation. The surface function should be differentiated with respect to u. Now we already have two vectors that are in the tangent plane of the surface. We are looking for a normal vector of this plane that will be also the normal vector of the surface. The cross product of the two vectors is always perpendicular to the two operands, so we use the cross product to calculate the normal vector. Summarizing, when we have a parametric surface and we need the normal vector, we obtain the partial derivative with respect to u and the other partial derivative with respect to v and calculate the cross product of the two partial derivatives. Let us consider examples also with their C++ implementation. So we will implement an evaluation function that takes the two parameters u and v, and in this implementation we assume that these lowercase u and v parameters are always normalized, so they are in the unit interval. This will allow us to handle different surfaces uniformly. Inside the function, the unit intervals are scaled up according to the real domain of the parameters of the particular surface. Our first example is the cylinder. The cylinder is an extruded surface and also a rotational surface, so we could use both strategies to develop a surface equation. Here we are going to use the strategy of extruding. So we need a profile curve. In case of a cylinder, the profile curve is a circle that is placed for the sake of simplicity on the xy plane. If the radius of this circle is r, then the equation of this circle is r times the cosine of the first free parameter and r times the sine of the first parameter, and we are in the xy plane, so the z coordinate is 0. The spine of the extruding operation is just a line segment that is in the direction of axis z, and it is parameterized by the second parameter v, so it runs from 0 up to the height of the cylinder. According to the observed rule of extruding, the parametric equation of the surface is just the addition of the equation. The parametric equation of the surface is just the addition of the parametric function of the profile curve and the spine curve, and if we add these two together, we can obtain the parametric equation of the cylinder. The domain of u is from 0 up to 2 pi because we want to have a complete circle, and the domain of v is 0 up to the height of the cylinder. Let us see the evaluation function. It gets the normalized uv and scales these normalized uv parameters up to the real range of the parameters that are denoted by uppercase U and V. The point corresponding to U and V are expressed in the profile curve, also called base curve, and on the spine curve. Then the two vectors are added. We will also need the normal vector of the cylinder at this point. It can be obtained using geometric considerations. In case of a circle, a vector pointing from the center to one particular point on the circle is always perpendicular to the circle itself. The normal vector on the xy plane is just the position vector of the point where the normal vector is needed. When this base curve is extruded, so when we apply a translational motion, this translational motion doesn't change the normal vector. So no matter where we are, what value this v parameter has, the normal vector remains the same as was calculated for v equals 0. Our second example is the torus. The torus can be imagined as a rotational surface. Here the profile curve is just a circle of radius lowercase r, and its center is at distance uppercase r from the origin of our coordinate system. This circle is parameterized with parameter u, so the range of u is 0 up to 2 pi. First we express the profile curve as a parametric curve of u. We use the parametric equation of the circle, so lowercase r times cosine u and lowercase r times sine u expresses a circle on the xz plane with center being in the origin of the coordinate system. If we translate it along axis x with distance uppercase r, then we can place our red circle here. In the second step of the creation of rotational surfaces, the points of the profile curve execute a circular motion. We rotate it around axis z, so from a single point we have another curve, so which is parameterized by free parameter v. The radius of this black circle is here. The distance between the profile point and axis z, and this radius is multiplied by cosine v and sine v according to the parametric equation of the circle. So in this way we can express the xy Cartesian coordinates of the surface, which is the rotation of another circle. If we rotate around axis z, the z coordinate doesn't change, so we just copy what we have obtained when considering just a single point of the profile curve, so the z coordinate will be lowercase r times sine u. both the profile curve and the circle resulted in by the circular motion are full circles. So both parameters have a domain that are the 0 to 2 pi interval. The evaluation function of the torus is just the computer implementation of these three formulae and also the computation of the normal vector at a particular UV parameter pair. Although we could use geometric arguments to find the normal vector of the torus, here I want to demonstrate how the dual numbers can be used to help the evaluation of a normal vector at a particular point. Generally, the normal vector is the cross product of the partial derivative with respect to u with the partial derivative with respect to v. So we need two derivations. The dual numbers are invented to help this derivation calculation. We use a version of our dual numbers where the derivative is a vec2 type, that is, it has two components, because now we have two variate functions and we are interested in the partial derivative with respect to the first and also in the partial derivative with respect to the second variable. So when we look at one Cartesian coordinate, the coordinate depends on two variables, therefore we will have two derivatives. Again, the lowercase uv parameters are normalized, so from these normalized parameters we should obtain the uppercase uv real parameters by scaling up the normalized parameters. The derivatives will also be needed, so these parameters will be dual numbers with two derivative values. When u is initialized, its value is u times 2 pi and it has two derivatives. The first derivative of u with respect to the first derivation variable, which is u, is 1. And the first derivative of u with the second derivation variable, which is v, is 0. Similarly, the second parameter is also a dual number. Its value is v times 2 pi, and concerning the derivative values, the derivative of v with respect to the first derivation variable, that is, with respect to u, is 0, and the derivative of v with respect to v is 1. The radius of the circular motion shows up both in the formula of x and y, so it's enough to calculate this common term only once. We denote it with d. d is the cosine of u multiplied by lowercase r, and we add the uppercase r value. We have to use the cosine function with uppercase initial because we want that version that expects dual numbers and also outputs dual number. When d is available, we can evaluate the Cartesian coordinates by the direct implementation of the developed formulae. So for example, x is just d times cosine v, y is d times sine v, and z is sine u multiplied by lowercase r. Thanks to dual numbers, when these expressions are evaluated, we have not only the values of x, y, z, but also the derivatives with respect to u and with respect to v. From x, y, z, we can fetch the value referring to the f data member of the dual number class. The derivatives are in the d data member, but the derivative is a vec2 type, so it has two components, x and y, and x components store the derivative with respect to u, and the y components store the derivative with respect to v. The normal vector is the cross product of these two partial derivatives. Our final example in this category is the Möbius strip. The Möbius strip is like a cylinder or a ring, but we apply a 180-degree rotation. This is a wedding ring, but very uncomfortable one, but at least shows the nice properties of the Möbius strip. Here you can see a Möbius strip and several tori traveling along it. We can also experience the feeling of traveling along a Möbius strip. The equation of the Möbius strip is quite similar to the equation of the cylinder, but instead of using V directly, a 180-degree rotation is also added. In order to visualize Möbius strip, we need to implement the evaluation function. Parameters uppercase U and V will be dual numbers because we will also have to compute the derivatives with respect to the parameters. The domain of U is 0 up to pi because we want to apply a 180-degree rotation when the end of the strip is attached to the beginning, and V is responsible for the width of the Möbius strip, so it goes from the negative half width up to the positive half width. The first parameter gets the value multiplying the unit interval by pi. It is the first derivation variable, so the derivative with respect to the first derivation variable is 1 and the derivative with respect to the second derivation variable is 0. V gets the value from normalized lowercase v by scaling up according to the domain of the real V, and this is the second derivative variable. The three formulae of the Möbius strip is just copied, and all parameters are evaluated for dual numbers, so the results will also be available in dual numbers. From a dual number we can fetch the value by referring to the f data member, and we can fetch the derivatives by referring to the d data member. The derivatives are VEC2 again because now we also talk of two-variate functions. The x components of these VEC2 derivative identify the derivative with respect to u. The second components, the y components, identify the derivative with respect to v. And again, the normal vector is just the cross product of the two partial derivatives. So far we traced back the definition of surfaces to the definition of curves, and these curves can be analytically defined curves or free-form curves specified, for example, with the strategy of Cat-Mouron splines, Bezier curves, Lagrange interpolation curves, anything we want. Free-form curves are defined by control points. Using this approach, we can also say that all surface definitions will require the specification of control points from which the curves and finally the surfaces are built. This is the strategy of free-form surface design, which can be imagined as a direct generalization of the definition of free-form curves. Suppose we are looking for the definition of a surface that is a two-variate parametric function. From these two variates, let us fix one, for example, variable v, while we allow the other parameter to change. So this is a scalar parameter vector-valued function, which is a curve. And this curve is on the surface. Such curves can be conveniently defined with control points, using, for example, Bezier approach or Cat-Mouron approach, whatever. This curve is specified by these red control points and with some weighting function system that depends on the type of the curve. With this, we identified one curve on the surface. This curve is also called Isoparametric Curve because from the two parameters, one parameter, namely v in this case, was fixed. If we want to consider another isoparametric curve where v is fixed differently, then we could use the same strategy, but in that case the curve should be identified by a different set of control points. So we can also say that the first level red control points will be functions of parameter v, and if we modify v, then the red control points also go along a path, or in other words, a curve. We are very good at defining curves. This curve, that is the path of the red control point, can also be specified by additional control points, the green control points in this figure, and with some strategy which has associated weighting functions. The control point will be a function of v, and this function is the combination of the second level control points rij. The weighting of this combination is defined by the actual type of the curve. Substituting the formula of the first level control points into the previous equation, we can express the two-variate surface equation as the combination of a two-dimensional grid of control points where the weighting functions are the products of the curve weighting functions. One is parameterized with v and the other is parameterized with u. So if we use, for example, the Bernstein polynomials as weighting functions, we will get Bezier surfaces. If we use the Lagrange weighting functions, then we can get Lagrange interpolation surfaces. In fact, all properties of the curves are automatically inherited by the surface if we use their weighting functions. Surface design with this strategy can be imagined as placing many control points over the surface, and if we are not satisfied with the shape of the surface, the control points nearby the unacceptable surface region is modified. Let us see a concrete example of a Bezier surface where we have 16 control points, and the Bezier surface is visualized here with its side views and top views and also a perspective view. We can modify control points one by one. You can imagine that this is a quite tiring process, but sooner or later we could get something which reflects our expectations. Okay, this concludes our chapter on surface definition. Thanks for your attention.